Hi, my name is Demi Obenour. I'm from Invisible Things Lab, and I'm here to talk about reasonably secure GPU acceleration without fancy enterprise GPUs. I'll start with the introduction, then go over the... Is this not working? Okay, sorry. Then I'll go over the importance of GPU acceleration, some of the various options that are available, some security considerations, plans for implementing this, the relevance to enterprise servers, and finally the conclusion. Okay, GPU and acceleration and untrusted guests, the elephant in the room, so to speak, of virtual graphics. The prevailing wisdom is to only give GPU access to trusted guests. But in client systems, the VMs that need GPU access are usually not trusted. They could be things like a VM you're doing video editing on a video that you're collaborating with someone else, and someone else might have accidentally wound up getting that video compromised with an exploit. Or it might be a VM you're doing untrusted video games in, or something like that. The result is that users of systems like CubesOS either wind up resorting to workarounds that are of questionable security, they buy a whole nother computer, or they just give up. Those workarounds might be things like PCI pass-through of something where we can't guarantee no unwanted persistence. This talk is a proposal for providing GPU acceleration to untrusted guests in a reasonably secure and supportable way. Requirements for GPU acceleration on clients. The biggest one is that your enterprise GPUs aren't available. You're stuck with consumer GPUs. Also, many VMs will typically need, or at least benefit from, GPU acceleration, and covert channels are out of scope. That means that static partitioning of resources, as you'd want in like a cloud setting, is neither needed nor desirable. It's unneeded because covert channels are out of scope, and it's not desirable because users don't want to have to say, this VM gets X amount of the GPU and X amount of VRAM and so on. Also, denial of service is only a minor concern, and that's basically why this whole thing can be done at all. A note on terminology. Obviously, as a type 1 hypervisor, Zen doesn't have the concept of a host OS. So for the purpose of this talk, I'm going to say that the host is the domain that already has a GPU, and the guest is the domain that is asking the host to run commands on that GPU. The host doesn't have to be DOM0. It often will be, I suspect, but it doesn't have to be. And the GPU can be a physical GPU, but if your GPU supports SRIOV, it can also be a virtual function. And that means that So basically, you can compose some of these techniques. GPUs on the client side are becoming more important, not just for things like gaming or video decoding, as Ray showed, but also just for general applications, especially if you care about them being responsive. Display resolution is increasing. That means there's more pixels to render. Also, high dynamic range means that color depths are going up, so there's more bits per pixel. And compared to a CPU, a GPU has more compute power, it's got more memory bandwidth, and it's got dedicated fixed function hardware to accelerate rendering. A mid-2010s Intel iGPU can render as quickly as an Apple M1 CPU, and it uses a lot less power. So you want to be able to use the GPU if it's there, and it pretty much always will be there. Furthermore, toolkits just assume that a GPU is usable. Both GTK4 and Qt Quick use OpenGL or Vulkan by default. And for 99% of users, this is a good thing. New Qt apps generally use Qt Quick, which uses GPU rendering, instead of Qt Widgets, which was rendered in software. And without GPU access, applications fall back to slow software emulation. So what are the various GPU acceleration options? There's IOMMU-based solutions, PCI pass-through, and SRIOV. And then there's pure software ones, user space API forwarding, mediated devices, and VirtIO GPU native contexts. PCI pass-through assigns the whole GPU to a single VM, and Zen already has support for it. Sounds great, but it only allows one VM to use the GPU, which isn't enough. And there's other issues too. The good news is that if you're a cloud provider and you have control over the hardware and firmware, you can make this secure enough for public clouds with hostile users. The bad news is that for the rest of us, hardware infection is often a fatal threat. That could be things like overwriting option ROMs that will then be executed on the next reboot, or abusing the ability of an integrated GPU to communicate with a privileged coprocessor on the system, which isn't great. SRIOV is also used in some cloud environments. It's considered secure if it's implemented properly. Whether it is implemented properly is a matter of debate. But it also requires hardware and driver support. And on Linux, such support is generally lacking. For the only GPUs that have SRIOV in the official Linux driver and that aren't end of life are Intel Z2 GPUs. That means Lunar Lake and later for integrated ones, and possibly Battle Mage and later for discrete ones. I'm not sure if discrete GPUs are actually going to get SRIOV or not. I know the integrated ones do. Well, non-Intel GPUs either do not support SRIOV at all. They require drivers that are either closed source, that would be NVIDIA, or just aren't publicly available at all, that would be AMD. Or in the case of some really old AMD GPUs, they're end of life. Also, Intel Z1 GPUs do support SRIOV, but the official driver for them is i915, which doesn't. User space API forwarding is VirGL, Venus, GFX Stream, things like that. Ray Huang demonstrated it in the last talk, and as he showed, it has a substantial performance overhead, but even worse, it's got security problems. The nice thing about it is that the API it exposes is hardware independent, so you can virtualize a lot of different kinds of GPUs without having to put in new work for each kind. VirGL and Venus work with any GPU that has the appropriate support in Mesa. And to the best of my understanding, GFX Stream works with any GPU driver at all, including ones that are proprietary. But this is not a reasonably secure solution. The shader compiler and the runtime are on the host. And the user space API, which is now exposed to untrusted input from the guest, is not a security boundary. So you've got the situation where you're passing untrusted input to something that's not supposed to be secure against that. Oops. Mediated devices, this is things like ZenGT and libvf.io. This is where you expose a partially emulated GPU. You pass through performance-critical operations and trap and emulate the rest. Kind of like classic CPU virtualization. The guest may use a balloon driver to avoid address translation issues. Otherwise, the guest uses an unmodified driver. So it's kind of nice if you have to support a guest for which you can't trade the driver, like Windows. But this has too much attack surface also. The complex emulation logic is on the host, and in the case of ZenGT, it actually ran in the DOM0 kernel. I think this is because it had to virtualize the GPU for DOM0 as well. And also the trend is to move away from this technology. Intel replaced GVTG, which is what ZenGT used, with hardware SRIOV in their later chips. The focus of this talk is VirtIO GPU native contexts. These forward the hardware-dependent kernel driver API. This is already a security boundary because user space to kernel on Linux is also a security boundary. Whether we trust it enough, that's another question, but it is a security boundary. Also, this API changes very slowly, and it's crossed rarely. It changes very slowly because Linux has very strong guarantees about compatibility, and it's crossed rarely because user space API calls to OpenGL, OpenCL, or Vulkan functions are much less common than system calls, or much more common than system calls are. Furthermore, you can make this API asynchronous. And what that means is that instead of saying, hey, do this and give me the result, you say, do this, put the result here, and if there's an error, well, we just crash. Which actually works fine so long as there's no error, and almost all the time there will be no error. So that means that you can batch queue commands in the guest and not have to wait for the results. At least on Chromebooks in benchmarks that Rob Clark did a while back, he found that 90% of native performance is expected and that 98% was typical. Now, the results for AMD that Ray Huang posted aren't as good, but they're still really good compared to other virtualization solutions. And resource assignment is fully dynamic. That's good because it means the users don't have to provide any extra information up front, which most users aren't going to want to provide, and that non-technical users aren't going to be able to provide decent defaults for. So what systems can use this? Well, this is already shipping in Chromebooks for Qualcomm GPUs. Just checking the time, sorry. Yeah, using the MSM kernel driver. It's currently being upstreamed for Intel, AMD, and Apple GPUs. Yes, the Asahi project is going to use this as well. It's their main plan for gaming on Asahi. Other GPUs aren't yet implemented. They could be implemented, though. You could implement support for NVIDIA. It's just no one's done it yet. But there's no fundamental obstacle. Also, only Linux guests are supported right now. But again, that's just a case of no one has implemented support for other guest OSs yet. But you could. There is an experimental Windows VirtIO GPU driver, but there's no native context support. The big thing that you'd have to do for a Windows port is run Mesa on Windows, but I think you can already kind of do that-ish. This is the basic native context architecture. You've got the guest, which speaks VirtIO GPU protocol to the server, which then makes ioctls to the GPU driver. The driver then passes buffers to the server, which then passes them to the guest, and page faults in these buffers are handled by the driver. And that's what makes memory management for VirtIO GPU different than, say, a PV driver. Security considerations. I said this was going to be used for untrusted guests, so it obviously had better be secure. So what are the security boundaries and what aren't? The security boundaries are that a guest cannot compromise the host or each other. Guests cannot obtain sensitive data from the host or each other. And the host doesn't get control over the whole system if it didn't have it already. And that means that the host doesn't, for this purpose, doesn't have to be DOM0. It only has to have privileges over the domains that it's providing VirtIO GPU to. The things that are allowed that aren't security boundaries are that a host has full control over its guests. Denial of service, which is usually, hopefully temporary, is possible. And covert channels are possible. What kind of security can we get in practice? This heavily depends on things outside Zen's control. Zen doesn't make the VirtIO GPU native context implementation. It doesn't make the kernel mode driver. And it doesn't make the GPU firmware or hardware. So my proposal here is to delimit at the rutabaga GFX API boundary. Rutabaga GFX being a user space library that is used for this. Specifically have it that Zen project is responsible for the secure use of this library, but others are responsible for ensuring that Rutabaga GFX and the code that it calls are secure. Now onto the types of vulnerabilities and types of attacks. Denial of service is the least serious, but unfortunately in the GPU world, it is unpreventable. A malicious or even just buggy guest can force the GPU to reset. That's unfortunately with current GPUs a fact of life. The result is denial of service to other workloads on the GPU. There may be ways to make it less likely that other contexts get killed, but it can't be prevented. At least that's what my understanding. My understanding is also that AMD discrete GPUs generally struggle with partial resets and wind up clobbering all of VRAM. But most desktop systems accept this risk because it's that or do all your rendering in software, and this risk is generally considered the lesser evil. Workloads that aren't using the GPU aren't going to be affected. And if your workload uses robust context, it should be able to recover. On the Wayland compositor side, that means KWin. Workloads that aren't using robustness won't recover, but not using robust context is something that can be fixed in the workload side. So if you care about your workloads recovering, make sure they use robust context. Information leaks. GPUs have often failed to clear data between contexts. For context here, pun sort of intended, a context on the GPU is the equivalent of a process on the CPU. It's the unit of security, it's the unit of isolation, and it's the thing that can, at least in theory, be killed without affecting anything else. And it maps to an address space. So not clearing data between contexts is bad. It would be like your CPU, it would be like your kernel it'd be like if your kernel gave you uninitialized memory containing junk that might contain sensitive data. NVIDIA had CUDA leak, Intel had iGPU leak, and then more recently there were leftover locals and whispering pixels, both of which affected several vendors. The way to make sure that this isn't an issue for you is to ensure that your GPU firmware driver combination isn't vulnerable. CUDA leak and iGPU leak have both been patched for years. For leftover locals and whispering pixels, you need to ensure that your system is either patched or isn't affected. I believe for AMD, patches for leftover locals will be coming out in 2020, in July, so next month. Last and worst, privilege escalation, when the guest can take control of the host. These are almost entirely due to memory unsafety issues in the driver, but they're sometimes due to firmware problems. Native contexts actually mitigate most of these because a lot of them are things like race conditions or certain kinds of failure to properly validate inputs. And with native contexts, ioctls are serialized and the inputs are somewhat pre-validated. You aren't going to be the native context code won't pass a junk file descriptor. Rob Clark of Chrome OS says that about 80% of the vulnerabilities are mitigated that way. For i915, it's looked to be a bit less, probably because i915 is an older, more complex driver, but also maybe because I was considering ioctls that might be exclusive to the compositor or something like that. The way to prevent this is to keep your kernel and firmware up to date. Newer drivers should hopefully have fewer vulnerabilities once they're mature, for the simple reason that they're simpler. i915 is a fairly old driver that deals with has a lot of legacy stuff in it. Security process. Zen has a world-class security process. Detailed advisories, back patches are backported, and there's a pre-disclosure list. The graphics stack currently lacks a good security process, but there's interest in improving this, including from Chrome OS security. Mapping host pages into the guest. This is the first of the implementation plans I'm going to talk about. And this is how a VirtIO GPU is really different than a traditional PV driver. With a traditional PV driver, the guest allocates pin memory, the front end, the back end maps it using grant tables, and then the back end releases that memory when it's done. With VirtIO GPU, the host allocates memory that's not pinned. It maps it into an emulated PCI bar. It can page it at will, and it can revoke the mapping, and it must handle page faults. Why is VirtIO GPU different? Because the only way to allocate GPU-accessible memory is via the GPU driver. The pages might need to be in VRAM rather than in system RAM, or they might have different caching attributes. Furthermore, GPU memory is pageable. The kernel driver is allowed to move pages at will and can revoke access whenever it wants. Pinning memory used by a GPU, at least I've been told it doesn't work in general. It might work in some specific cases. But as Ray Huang said, Zenya Rajiadaku is working on a solution. It's going to require host kernel changes and hypervisor changes as well. But it might also make it easier to write user space VMMs for Zen, because you'll be able to use better APIs to provide guests with memory. Rutabaga GFX and VirGL Renderer are virtual graphics and Wayland libraries, and they're what actually talks to the GPU driver and the Wayland compositor. VirGL Renderer is used by VMMs for accelerated virtual graphics. It supports VirtIO GPU, including native context, and it's currently written in C, but the native context code may get rewritten in Rust. Rutabaga GFX is a Rust library. It's part of CrossVM. It uses VirGL Renderer, and it also supports Wayland pass-through, which is really important for things that want seamless virtualization like Cubes does. It also provides a stable C API. So the guest needs to be able to, somehow commands from the guests need to get to Rutabaga GFX for it to do its job. You can either use QEMU for that, or you can use something else. But QEMU should be avoided, because it's lots of C attack surface, and you can't use a stub domain if you're using GPU acceleration. Cubes currently uses a stub domain, but if you're using GPU acceleration, then you can't use a stub domain because the stub domain doesn't have the GPU driver. You're back where you started. QEMU can be deprivileged, but that is not officially a security boundary, even though I'm told that it was designed as one. Furthermore, Zen PV, which is what's currently used for DOM0 on x86, makes sandboxing either difficult, expensive, or both because of speculation issues. If you want the details, ask Andrew. A better solution is to use something memory safe. That's less likely to have exploitable vulnerabilities, and it could be Rust VMM, or it could be something standalone. Based on Rust VMM, I mean. Rust VMM, for context, is a set of Rust libraries for writing QEMU-like things. How are we going to see the results of this work? Because, yes, you can use a GPU for compute, but in a client system, you really want to use it for graphics. And that means you want to see the results of what you're doing. That means you need guest integration and host integration. On the guest side, there's a couple of options. There's Sommelier, which is C++, and Wayland Proxy Vert WL, which is OCaml. Wayland Proxy Vert WL is the much better choice, according to people who've worked with both. and adding GPU acceleration support to it should be quite easy. On the host side, Rutabaga GFX already provides Wayland pass-through, but it needs a Wayland socket to connect to. And so that brings up the question of, are you willing to expose your Wayland compositor on the host to your guest? And that, for something where your host Wayland compositor is known to be secure against hostile input, and where you can trust, that it isn't going to be popped, and where it doesn't expose sensitive protocols like capturing the screen, then that might be fine. But if you can't, then you can use Wayland Proxyvert WL's ability to do protocol filtering. Could this be used in enterprises? Yes, at least in some cases. It's useful to limit the blast radius of an exploit or for time sharing, and you might be able to virtualize AMD or Intel compute nodes. And it should work with Linux VDI, but the caveats are that denial of service is still a risk, and NVIDIA and Windows support aren't implemented yet. Conclusion: GPU acceleration is critical for modern client systems, and it can be provided in a reasonably secure way even without hardware SRIOV. So we can move past only give GPU access to trusted guests. Thank you. Are there any questions?
Would there be an easy way to get Windows support with a two-step, like getting command streaming from Windows to an intermediate Linux guest that would be using context or something?
Probably yes. I don't think anyone's tried it, but I also see no reason it can't be done. So I'm going to say the answer is, again, somebody needs to do it, but it should be doable. Any other questions?
Denial service. Would it be possible to try to blacklist the guest that blocks the GPU and then try to reset the GPU in the world?
Hopefully. Unfortunately, there are cases where there are at least bug reports of this thing crashed my whole system and I had to reboot. But most of the time, it should be possible to do what you said. The kernel does, yeah. Marek?
Related to that, can you reliably tell which context crashed the GPU?
You should be able to. If it's something like a fault or a timeout, you can. If it's something like the GPU was underpowered or overheated and had undefined behavior, then no. But hopefully that should... Yeah.
At that point, you've got a system problem anyway.
Yes, exactly. Any other questions? Whichever, Alejandro?
So you mentioned before that guests were just able to issue GPU resets. Is that to the whole card?
No, guests can cause the GPU to reset.
It's that the problem is that GPUs aren't preemptible, at least if you're using them for graphics as opposed to compute. They just don't support preemption. The best you can do is just blow away this current state. And that will kill at least the current context and probably anything else that's running on the GPU at the time. You might be able to limit the blast radius by ensuring that only one context is executing at a time.
Once the GPU is started and the command is not back in the southern timeline, then we will trigger GPU reset. It is from the kernel side. If the command advance not back on time,
Yeah. Oh.
then the driver will automatically trigger GPU recovery in back. But we cannot promise every time the GPU recovery can be successful. This depends on the GPU other side, which they are having.
Which what? Which fault? Okay. What if it's something like a shader? Can you promise it in the case of a shader is looping forever or a shader access junk memory?
If the shader just looking in the harm probably causes many problems. If the hard problems can probably be most of the time we cannot recover successfully.
If it's a hardware problem? I'm assuming that that it's not a hardware problem because you could also have hardware problems on the CPU.
Most of the time, it actually doesn't work. Yeah.
Okay, good. George,
I was just gonna ask how much this was done.
how much of this was how much of this was done? Well, it's shipping on Chromebooks with KVM. The parts that haven't been done are the Zen integration, the user space VMM that's not QEMU for Zen, and the Wayland. And I think those are the big things that haven't been done. Ray?
Yeah, actually, during the last XDC, I talked with the Rob Clark, it
Yeah.
is the native complex order.
Yeah.
He also mentioned we probably have to start some separate program, use the virtual native context. So do you have any suggestion or idea to improve the native context way?
You mean in terms of security? Or in
I just want to let you all know that the break does end at 11:05 in the next session, so maybe if there's like a way to take this conversation.
yeah, I'll take that as